Hello everyone, my name is Noah Langenfeld, and in this talk I'm going to be discussing the maintenance of nutrient solutions for recirculating hydroponic culture. We're going to start off with this universally loved recycling logo that really kind of embodies the essence of this talk. I'm going to talk about how we develop and maintain nutrient solutions so that we can continually recycle and recirculate the solution throughout the entire life cycle of the plant. We don't have to dump out the entire tank and refill it with fresh solution. We can just top it off as necessary and the plants grow perfectly. I do want to acknowledge some of our funders. So NASA is a big one. We've been grateful here at the lab to be funded by NASA for about 40 years now. We do a lot of research with growing for advanced life support systems, both in the International Space Station and low Earth orbit things, and then also for future journeys to the Moon, Mars, and beyond. And also, of course, our laboratory. That's where we're actually filming this video right now. We're in the Crop Physiology Laboratory, and we're here at Utah State University in Logan, Utah, which is at the far northern end of the state. And finally, my co-authors here, Lauren Payne and Dr. Bruce Bugby. So we're going to start off really simple. This is just a basic diagram of a plant here. We've got the plant growing out of its container and the roots growing down into the container. And again, this is representing deep flow hydroponics. So the roots are constantly submerged in the water. We maintain that level at a constant level throughout the entire life cycle. So we're checking these tanks almost every single day and topping them off with refill solution as necessary. So just the basic principle here, the water goes in the tank, the water gets sucked up by the roots, and then it's transpired by the leaves. Everyone knows this, but we just have to kind of have this as a framework for what we're going to talk about. Because we don't just have water in the tank. Plants can't grow on just water. We have to add nutrients. That's represented here in the yellow arrow. So the nutrients are dissolved in the solution, so they get taken up with the water. However, the nutrients get stuck in the biomass of the plant. They're not transpired. The nutrients don't leave the plant. Once they get sucked up, they're in the plant. So that will then give us a ratio of each nutrient in the plant per the total biomass of the plant. And that is one of the main things that we're looking for to help us develop these solutions. So we're looking at that desired tissue concentration. So for whatever element it is, if it's nitrogen, for example, maybe we want something like 3% nitrogen in the tissue. So we want 3% nitrogen per gram of biomass, or 0.03 grams of nitrogen per gram of biomass. We're going to take that value and we're going to multiply it by the water use efficiency. So the water use efficiency, that's the grams of biomass produced per liter of water transpired. So when we use a closed system like this, deep flow hydroponics, we can accurately measure how much water we have added to the system, and we assume there's no evaporation. All water that we add is transpired through the plant. And then of course at the end of the study, we're going to weigh the plant, get the dry biomass, and that gives us our water use efficiency. We multiply those together, and that gives us what our solution concentration should be. So the desired tissue concentration, that's going to be pretty constant across most plants, most species. The water use efficiency is going to change though. It's definitely location dependent. I'm going to show you some numbers in a little bit here. We're in Logan, Utah, so it's high elevation, pretty dry, relatively low humidity. We don't enrich with CO2 at all. So all these factors play into water use efficiency. High CO2, you're going to have a higher water use efficiency. Higher humidity, also higher water use efficiency. You're not transpiring as much water. So that does have to be taken into consideration for your specific location and crop that you're going to be growing. So here's some of the crops that we typically grow. First off, we have the lettuce. Lettuce is commonly grown in hydroponics throughout the country here and frankly throughout the entire world. It grows really well in hydroponics. As you can see, I have up here 30 days. So we can seed our lettuce and 30 days later it is ready to harvest. Super efficient, super fast growing crop. We like to say it's the Ferrari of the plant world around here. That has a water use efficiency of about 3.3 grams per liter. So again, for every liter of water that is transpired, the plant is going to gain 3.3 grams of dry biomass. Next up we have wheat. We grow a lot of wheat here. NASA is really interested in wheat, specifically for growing in space. Obviously, commercially, wheat is grown in the field. It's not grown in hydroponics, but does provide a good example of a little bit of a longer crop. This is a super dwarf variety we have here called apogee. It goes from about seed to harvest in about 60 days, so twice as long as the lettuce. It has a little bit of a higher water use efficiency. We've measured about 3.5 grams per liter on average. And finally, tomato. Tomato is also a commonly grown crop in hydroponics. Here, tomato it typically takes about 3 or 4 months to reach full maturity for us. So again, much longer than the other two crops. It also has a higher water use efficiency that we've seen, about 3.8 grams per liter. So you can see we just got the tops of the plants here, and then using the liquid deep flow hydroponics, we can accurately get a sense of what the roots look like. We can weigh the roots, we can monitor them on a daily basis, so it really works well for us. So let's take what we've discussed now and actually put some numbers and kind of walk through a couple of different examples. So up here we just have that same equation that we first started with. We've got the desired tissue concentration times the water use efficiency. That equals the solution concentration. So let's put some numbers in here. So let's do an example for nitrogen. Say that we want 3% N in our leaves. So that's going to be our desired tissue concentration. So that's 0.03 grams of N per gram of biomass. We're going to multiply that by our water use efficiency. I'm just going to use the average value that you saw on the last slide. So that's 3.5 grams of biomass per liter of water transpired. All we do is we multiply those two together, and we get 105 milligrams of N per liter of water. That's about 105 ppm N. So you can see these units, they just cancel out. It's just a simple multiplication step. We got 0.03 times 3.5. That gets us our 105 ppm N. So that might seem a little low to some people. It's kind of just at the edge of just what we consider adequate for nitrogen. So let's change up some of these numbers here. So let's say we have 4% N, or we want 4% N in the leaf tissue, and that gives us to 0.04 grams of N per gram of biomass. And let's say our water use efficiency is a little bit higher, say 4 grams per liter. So we multiply those two together, we get 160 now milligrams of N per liter of water. And that's about 160 ppm N. So almost every single fertilizer that you're going to see on the market is between these two numbers, 105 and 160. Honestly, 160 is probably excessive. Optimal is probably about maybe 120 to 130. That's kind of the sweet spot that we've seen for N fertilizer. We typically stick more towards the lower end because we're going to use pH control. We're going to add additional N by pH control, which we'll talk about in a little bit. So this doesn't only apply for things like nitrogen, phosphorus, potassium. We can also do it with micronutrients. So we'll take a micronutrient example here. We've got manganese. So we're going to shoot for, let's say, 60 micrograms of manganese per gram of biomass. And that's just ppm. We want 60 ppm manganese in the leaves. We're going to take that again by our average water use efficiency here, so 3.5 grams per liter. Multiply that out. We get 210 micrograms of manganese per liter of water. And that comes out to 0.21 ppm manganese. So when we design our solution, we're going to shoot for 0.21 ppm manganese in the solution if we want to achieve 60 ppm in the tissue, and our water use efficiency is 3.5 grams per liter. Again, all these cancel out. It's just the same exact multiplication step over and over and over. I did a few unit conversions here with micrograms to grams, but for the most part, it's a pretty simple process. So I mentioned pH control. pH control is very important in deep flow hydroponics, mainly because this solution here is very poorly buffered. It's mainly just deionized water, and then we add our nutrients to there. There's not really much of a buffer. There's a little bit of phosphoric acid, but not enough to do much buffering. So we have to have an automated system of pH control. So we're kind of going back to our tank here. We've got 2 plants growing in the tank, and we've got this pH electrode in the tank. It's in there 24/7 throughout the entire time of the study. That pH electrode is connected to a pH controller. This controller will take the signal from the pH electrode and compare it to its set point. If the controller thinks that or senses that the pH is above or below its set point, it's going to dose with either acid or base depending on how you set it up. So in that sense, we can have it just dose a very small and frequent amount, and we can kind of keep that steady state pH going throughout the entire cycle of the plants. So how does that controller work? Well, the controller is connected to a solenoid valve, and that solenoid valve is connected to a column. We just make them straight out of PVC pipe, and that's filled with nitric acid or nitric acid and ammonium sulfate. We'll discuss that in just a second. But it's just a simple gravity-fed system. the electrode senses you've gone away from your set point, sends a signal to the controller opens the valve, and the solution goes in, hits the electrode, everything stops, cycle repeats. Pretty simple, but very important to maintain pH. And you say we have it maintained here at 5.8. We want to do 5.5 to 5.8, and that's what we found to be optimal. So nitrogen here, we've got two different forms of nitrogen. We've got nitrate and ammonium. This is a classic example in plant physiology. But as these are taken up into the plant, we have to maintain charge balance. So as nitrate is taken up into the plant, hydroxide is going to be released back into the solution. That's going to increase our pH. Ammonium's taken up into the plant, protons are going to be released back into the solution. That decreases the pH. That has consequences for our pH control. You might think these are taken up at the same rate, but they're not. Ammonium is taken up way faster than nitrate, so we really got to be careful and mindful of that when we're designing our solutions. The reason I said we have nitric acid or nitric acid and ammonium sulfate is because of this graph here. We can see on the bottom, that's when we control our pH with nitric acid and ammonium sulfate, and the blue line is when we control it just with nitric acid. So we end up using a lot more acid if we're just using nitric acid, but if we have that mixture of both end forms, they kind of fight each other back and forth and help stabilize the pH on their own, so we don't need to add as much solution. All right, let's look at one more thing here. We're going to look at tomato. So tomato, we're just kind of looking here at the time, the treatment time, and then our EC, millisiemens per centimeter. So EC, again, that's just the kind of the measure of the bulk nutrients in solution. It starts out here pretty even, and then all of a sudden the plants kind of start to hit that exponential growth phase, so they start drawing down nutrients. The nutrients go down in the solution. So there's a little bit of a difference here between nitrate and ammonium, that same pH control solution, and then just plain nitrate. So if they're fed just plain nitrate, they're going to draw that down quite a bit. But if they have a little bit of the ammonium in there, it's going to kind of stabilize, not quite as low as the nitrate, and eventually start increasing again. Kind of the theory behind that is if we have both forms of the nitrogen in there, the ammonium is taken up way faster, therefore the nitrate is not taken up. If the ammonium is taken up, things like calcium are probably going to remain in solution a little bit longer. Again, concepts of charge balance here. However, if we look at lettuce, both of those lines look pretty much identical. However, the thing to note here is the time of the treatment. So this treatment length, 80 days since transplanting. This one, about 25. If we were to take this graph and superimpose it on here, it would come out at about 25 days. It would look identical to the tomato graph. So that kind of just shows the power of putting both forms of nitrogen into your nutrient solution. All right, and finally, just kind of a side note here, I mentioned wheat at the beginning of the presentation, but wheat is kind of unique in terms of crops. So things like lettuce, it doesn't produce seeds, at least we don't want it to produce seeds. We're only eating the vegetative part. But wheat, on the other hand, halfway through its life cycle, it starts producing seeds. So what are seeds made of? They're mainly made of starch. Not a whole lot of nutrients going on in there. So all that we see is that the nutrient, or the EC, remains pretty stable, and then it starts to increase at the end of the life cycle. So we switch to a different refill solution that has a much lower EC, but it still keeps increasing. Again, it's not really taking up any nutrients. It doesn't need any nutrients. It's not growing at all. It's just producing seeds in the form of starch and fixing carbon. So that's why we kind of have a different kind of setup for wheat. So just a couple of takeaways then from this presentation. First off, solution recycling. Using this principle of mass balance, where we have our desired tissue concentration and our water use efficiency, we can calculate the concentration that we need in our solution. We also have steady state pH control. By using both forms of nitrogen in our pH control, not just nitric acid, they kind of help balance each other out and help stabilize the pH a lot better. We also have reduced pH control of volumes. So that was that graph that I showed. Again, both those forms kind of fighting each other back and forth. We don't need to really control pH as much because the chemistry does it on its own, so it's awesome. And then finally, this helps with small, frequent doses of ammonium. So some ammonium is good, way too much ammonium is bad. Again, plants take it up super fast, and it's just not good for their rhizosphere. So with that, I'd like to thank you for watching my talk.